let's talk about two different kinds of collisions here. We have elastic collisions and inelastic collisions. So first what I want to do is I want to review collisions in general and how collisions conserve momentum. And then we'll review kinetic energy. Because we have two different, we're going to classify collisions based on what happens with kinetic energy. And the bottom line is, during an elastic collision, we're going to see that kinetic energy is conserved as well as momentum. That is, we're not going to lose any kinetic energy. But in an inelastic collision, momentum will be conserved, but kinetic energy will be lost. Some of the kinetic energy will be transferred into the environment through heating. We're going to increase the thermal energy or the temperature of the environment. So let's get started. We talked about collisions in the last unit. And what is a collision? Well, we have one object here, object 1, and it has a mass, and it has an initial velocity. Okay, and we multiplied those together, and we said, okay, that's the initial momentum of object 1 is equal to its mass times its initial velocity. So let's say its velocity is to the right. And then maybe object 2, and it has a mass, it has an initial velocity as well, and maybe it's going the other way. And so we say the momentum the initial momentum of object 2 is equal to m2v2 initial. Okay, so these guys, when they collide, and we've done this several times. I don't want to do it over too many times in a row, but while they're colliding, right, they're applying equal and opposite forces to each other. Here's the force on object 1 due to the object 2 is equal, but in the opposite direction is the force of 2 on, or the force on object 2 from hitting object 1. Newton's third law says they apply for equal and opposite, equal in force, opposite in direction. We multiply that by the time it takes, and that this is the impulse on object 1. We said the impulse momentum theorem says that this impulse is the change in momentum of object 1 is equal but in the opposite direction as the impulse on object 2, which means if I add these two together, I get 0 change in momentum. So even though object 1 gets its momentum changed, object 2 gets its momentum changed, but if I were to add those momentum together, I would get 0. Which means that the initial momentum of the system is equal to the final momentum of the system. And we said this is true for all collisions. Okay, so that's what we said. So if object 1 and object 2 are in your system, and we're going to isolate these from the rest of the universe, you would start here. And then you would say, okay, well, look, M1, V1 initial equals, or plus, I should say, plus M2, V2 initial. Well, when they fly apart, will be equal to M1, V1 final plus M2, V2 final. And this is how we start, right? We look at, and then you look at the problem that you're doing and you're saying, where is the initial momentum? Well, you might have a problem where one object is moving and the other one isn't. The object that isn't moving has 0 momentum. So you just, don't worry about it. Maybe the objects after the collisions, they've stuck together. What does that mean? That means they have the same final velocity, which means we can factor it out, which means we just add the two masses together and multiply that by their final velocity, and that will be equal to the final momentum. So we can take this, which is fairly complicated, has 4 terms in it. Sometimes terms will disappear, or they will combine in some way to make it a little bit easier. Okay, so that's what we talked about. We talked about collisions and conservation of momentum. But look, these objects also have kinetic energy. So like K1 initial, the initial kinetic energy of object 1. It's 1/2 m1 v1 initial squared. That's its kinetic energy. Now what is kinetic energy? Well, look, somebody had to do work to make this ball, or whatever it is, go. You had to throw it. So in order to throw it, you had to apply a force through a distance. You had to do work on it. You had to transfer energy out of your body, or whatever the object was through the ball, and give it energy, the energy due to motion. So when you do work, you transfer energy from one system into another, from your arm into the ball, and now this ball has energy. And it can do things, right? If it hits something, it can do work on it. Well, the same is true with ball 2. Ball 2 has K2 initial equals 1/2 m1 v2, initial squared. And if I add these two together, you know, K1 initial plus K2 initial, well, that's the initial kinetic energy of my system. I'm going to add these two together. Now, listen very carefully to what I'm about to say. When you added, look at this right here. What is true about momentum? Momentum is a vector quantity. So if this object is moving, if object 1 is initially moving to the right, it's going to have positive momentum. This object will have negative momentum. And so when you add them together, you could actually even get 0, right? Because one's positive, one's negative. Or you can have negative momentum or positive momentum, but that negative or positive refers to the direction of it. But look at these kinetic energy terms. 1/2 mv squared, 1/2 mv squared. 1/2 isn't negative, it's just 1/2. Mass is never negative. No such thing as negative mass. And look what happens to velocity. It gets squared. The velocity squared. Here's what we mean by velocity squared. Raise your hand right now if you are in AM or AMA, or you took it last year. Okay, that's almost all of you. How many of you remember the scalar product? Because I know you've done vectors already, right? Yeah, okay. So scalar product. Here's what V1 initial squared really means. And by the way, this isn't really critical to what we're doing here. I'm just being very, very thorough and rigorous. If you have V1 initial squared, what does that mean? Well, when you square something, you're multiplying it by itself, aren't you? V1 initial times V1 initial. But velocity is a vector. But energy is a scalar. It has no direction associated with it. So when we say V1 initial squared, what we're actually doing is we're taking the dot product, or the scalar product, of the velocity vector with itself, and thus getting rid of its vector nature. We're getting rid of its direction. So remember what the scalar product is. It's the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between them. And what is the cosine between V1 initial and V1 initial? What's the angle between a vector and itself? What's the angle between this and this? 0, right? 0. And what's the cosine of 0? 1. So this just becomes V1 initial times V1 initial times the cosine of 0 degrees, which is 1. So it just becomes V1 initial squared. So when you see this, think of, we use the dot product on the velocity, and thus we have a scalar. And energy is a scalar quantity. Work is a scalar quantity. Kinetic energy is a scalar quantity. Gravitational potential energy is a scalar quantity. Elastic potential energy is a scalar quantity. It has no direction, only magnitude. Okay, so look, it's impossible for kinetic energy to be negative. Thus, if I add these two together, these will be positive. The initial kinetic energy of your system will either be zero, nothing's moving, it's pretty boring, or it's going to be a positive quantity. Okay, so, and that's what we said was kinetic energy. And then, of course, we could do the same thing with the final kinetic energy. Okay, final will just be the 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. You'll just add them together like that. Okay? Does it all make sense? Any questions? Okay. So, we've talked about collisions, we've talked about kinetic energy. Now we're going to take these two ideas and use them to classify two kinds of collisions. So, I want to talk about elastic collisions first. In an elastic collision, we have two conditions that are satisfied. The initial momentum will equal the final momentum. This is always true for all collisions. But in an elastic collision, we also conserve kinetic energy. So, now, elastic collisions are actually very rare. It's pretty hard to have two things smash into each other and fly apart and not create a little bit of sound or a little bit of heat. But they do happen when a proton hits another proton. That's an elastic collision. And we came pretty close with our little toy cars. Remember, we had a car like this, and we had a little spring deal on it, and then we crashed it into another car. And what happened when these two collided was the kinetic energy, as this car slowed down, let's say this car hits this one and this one was at rest. When this car hits, when car 1 hits car 2, car 1 slows down, and as it slows down, the force acting between them compresses a spring that's inside this car. And when that spring is compressed, we turn kinetic energy into elastic potential energy. And then the spring expands or pushes apart, and when it does, it turns that elastic potential energy back into kinetic energy, so that at the end, we have just as much kinetic energy as we had to begin with. Now, when we collided these cars, though, that was just an approximation, because when the cars hit, we created a little bit of sound, didn't we? And when you create sound, sound is energy leaving a system. It's spreading out in the vibrations of molecules into the environment. So yeah, we did lose a little tiny bit. But if we neglect that loss, we can say that essentially the initial kinetic energy was equal to the final kinetic energy. Very, very rare, but sometimes we have something that's really close to an elastic collision, so we approximate it with this model. So when we try to solve a problem, we go, okay, M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. So we would use this equation, apply it to the problem, but we could also apply this equation. 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared will be equal to 1/2 M1 V1 final squared plus 1/2 m2 v2 final squared. So that's a lot of stuff. Notice I have vector hats here, but no vector hats here. Now when you're looking at an elastic collision, you take a look at what's given and you use these as your basic equations, and then you do what you have to do algebraically to solve the problem. So those are elastic collisions. In an inelastic collision, and almost all collisions are at least a little bit inelastic, well, you still have momentum being conserved. Because none of that thought process we said where two objects collide and apply equal and opposite forces for equal times, that's Newton's third law, create equal and opposite impulses, equal and opposite changes in momentum, therefore the momentum is conserved. All that is still the same, even for an inelastic collision. But in an inelastic collision, you lose kinetic energy. That is, your initial kinetic energy will be greater than your final kinetic energy. Now, here's an example of that. Suppose you're stopped at a stoplight or a stop sign, there's a stop sign, thank you. And so you're stopped, and then coming up behind you, somebody doesn't see the stop sign and they rear end you. They rear end your car. So here's the big truck, big SUV, and here's your little smart car that's smushed in front of it. When they collided, lots of sound was given off. And next time you're in a collision like this, if you can, get out of your car and go feel the crunched up metal. And it'll feel a little bit warm. Just put your hand on your crushed up car. It'll be warm because it was permanently deformed, and the energy that you had that was in the kinetic energy of your system was used to deform the metal, but also make the atoms jiggle a little faster, raise the temperature of the metal. And thus we lost kinetic energy, and that's called an inelastic collision. Now some collisions are the most inelastic you can get, and they're called perfectly inelastic collisions, and a perfectly inelastic collision happens when the two objects stick together after the collision. So if you have two objects, like in this case, the van hits the smaller car and then they move off together as one mass. When that happens, you have lost the maximum possible amount of kinetic energy, and that's called an inelastic, perfectly inelastic collision. Now, what you're going to be asked to do in an inelastic collision is to find out how much the kinetic energy was lost. So you would just go like this. You would say delta K, which is equal to K final minus K initial. Now, what do you think is going to be true about this value, this in joules, if it's an inelastic collision? What's going to be true about delta K? Well, if K final is less than K initial, you're going to get a negative, negative whatever joules. You're going to get a negative answer. And what that means is we lost kinetic energy during that interaction. Now, that energy was not lost to the universe. It's still in the universe. Energy cannot be created or destroyed in any closed system. But you're changing where that energy exists in the universe. Look, before the collision, look at this, these two cars. Well, this car was at rest, but this van was moving. Nice, organized kinetic energy. And then, bam! Almost all the kinetic energy has been dispersed into the environment through the random motion of molecules. It's a mess. It's a mess that cannot be cleaned up. You can never get back. And that's what we mean by an increase in entropy. We're going to study that in the next unit on thermodynamics. But that's what's going on. So sometimes it'll ask you what fraction of the kinetic energy was lost. And so what you do is you just say, if they want a fraction, just put delta K over K initial. And that'll be the fraction, or if you make it a percentage, that'll be the percentage of energy lost. The negative sign in there means that the energy was lost from the system. So you're going to lose most of it. Like if you shoot a bullet into a block, that means, hey, most of the energy is going to be lost. So, let's summarize here. We said that we reviewed collisions, and we said that during a collision, momentum is conserved. We also reviewed what kinetic energy was. It's the energy that an object has because it has mass and it's moving. Well, if I look at an elastic collision, of course momentum will be conserved, but kinetic energy is conserved as well. And so we can expand it. This is the initial momentum, final momentum, initial kinetic energy, final kinetic energy. And I can use these equations to solve problems. It's just algebra 1. But if you have an inelastic collision, your initial kinetic energy will be greater than your final kinetic energy. And therefore, you're going to lose kinetic energy to the environment. You're going to heat up the environment a little bit. And you can figure out what delta K is by using this, and then figure out the percentage of energy lost there. Any questions on elastic versus inelastic collisions? Elastic collisions, momentum and kinetic energy are conserved. Inelastic collisions, momentum is always conserved, but kinetic energy is lost to the environment through heating. Remember, kinetic energy is lost. Energy is not lost. Energy is changed. It was from kinetic energy, some of it gets converted into thermal energy, the random motion of molecules in the environment, so on. All right. That is all.